Thank you. So, good morning, everybody. I would like, first of all, to thank the organizers for giving me this opportunity to stand here in front of you. I'm actually honored by this. And what I think is that I'm going to represent my own community, astronomy, in front of this amazing community. And we'll see where we actually have a cross match. So, I'm an astrophysicist. I have actually used a lot of machine learning and statistics in my work. I have also been training a lot of people into these tools, and I have a lot of experience with science outreach. And Periastron is an organization that can host all of this above. So this is just a very short introduction of what I have been doing. So in this talk, what I'm going to do, I will try to showcase how Python has actually transformed the field of astronomy in the last 2 decades. So usually, or not usually, but oftentimes, I structure my talk around the title. So I try to break down the title into terms and explain the terms. So the first is actually very easy. Python. We are in a PyCon, so fortunately, I don't have anything to say about Python, right? Let's go to the next one, astronomy. So I believe that everybody in this room has already an idea of what astronomy is, but I would like to frame it with you together now. So what I did, as a modern person, let's say, I asked Wikipedia and Perplexity, right? What is astronomy? They came back with these answers. Don't go through the text. I will help you highlight the important points. So what is astronomy? First of all, it's a science, right? One of the natural sciences we have. What does it study? Celestial objects and phenomena that are outside Earth's atmosphere. How does it do it? It uses mathematics, physics, chemistry, biology, computers, right? And another key point of astronomy, it is one of the oldest sciences. Why is that? I believe that most of you have been already in a beach during the summer or in a remote area. Even if you didn't do it this summer, you have done it in the past. So you have looked up in the sky and you saw something similar to that, right? This is the night sky from Athens to night, but okay, it's not possible to see that because of the light pollution. But this has been the view of the night sky more or less for millennia. Since the beginning, humans, they would just look up and they would wonder, what are all these stars? What are all these lights? Right? And these questions about what is in the night sky would continue. With time, what they did is they try to actually connect this, they try to connect this with their own experience, with their everyday life. They try to find patterns. This is not very visible, but actually they try to connect the night sky with what they knew, the local stories or the myths. And actually, this survives up to today. The official names of the constellations are driven by the ancient Greek mythology. Okay? So, this has been the case for thousands of years. At some point, at 1600, a guy named Galileo turned a telescope to the sky that changed the view of the night sky. He discovered new worlds. Like, since then, the advance of technology, both telescopes, instruments, computers, along with the advance of the science that accompanies the study of the night sky, has resulted in more and more amazing discoveries. Fast forward to today, this is an image, possibly the state-of-the-art of image that we can produce from ground-based telescopes. This is the facility known as Vera C. Rubin Observatory. It initialized like a month or so ago. And what you look here is part of the Vigo cluster of galaxies. So you can see these galaxies, spiral galaxies, some fainter ones, and actually what you see in the background, you may see a lot of point sources. Some of them are stars, but most of them, hundreds or thousands of them, are what we call background galaxies. They are so far that we cannot resolve them. This is about 55 million years ago. You know what that means? But when the start started, there were no humans here. This light traveled 50 million years to come here. Actually, human beings didn't exist in Earth back then. Let's come closer. This is an image of what we call Trifid and Lagoon Nebula in our own galaxy. You see amazing details about the gas and the dust in this region. These are regions that form new stars. And if we go a step, not a step, possibly many steps outside, we can take a look of an image from James Webb Space Telescope. This is the state of the art of space telescopes out there. It is the largest and the most modern telescope right now. And this is the image of Stephan's Quintet. This is a small group of galaxies that actually interact each other. You have one of these galaxies going through this one, and you have this, what we call collision of galaxies. And what you see here is amazing details about how stars and gas is moving through the interaction. Right. What else have we achieved so far? So, take a second. This is a busy image. Eyes on me, please, right? To help you, guide you through through this. So, what we have been observing so far is the universe in the optical. This is just a very small part of the electromagnetic spectrum. Over the last 100 years, we have developed instruments and technique to look at different wavelengths. So if we go to infrared or radio, we see cooler stuff. When we go to the other part, let's say at UV or X-ray, we see hotter components of the instrument of this galaxy, for example. So what does this tell us is that we have a different views if we look at different parts of the electromagnetic spectrum, and beyond that, if we include gravitational waves lately. So in modern astronomy, we need to take into consideration all possible information from all these range in order to understand the universe and the objects we are dealing with. Okay? So, good. That's a definition, more or less, of what astronomy nowadays is. I have put this in. So, what does it mean? How Python is included in this process? For this, we need to define first what an astronomer does in his everyday life, right? So, for this, I have put a small quiz. If you are willing, we can actually, let me see if this, I hope this is going to work. No, first, I will have to put this. If you open the QR code there, then you have 3 fields. You can put in what do you believe that an astronomer does. Whatever you think, verbs, nouns, whatever. And let's see what will be the outcome of the word cloud. Let me see, I can already see observe as the main keyword. Observes, study, analyze, measures, what else? White papers, thinking, look at the sky, assumptions, study galaxies, universe. Nice, research, not astrological predictions. Cool one. Thank you. Takes picture, discover Python, yeah. To fade, it will become bigger with time. Indeed. So, one of the main keywords was observe. That is correct, right? We do observe. So, this is a fellow colleague observing through a telescope. He is an astronomer, indeed. However, when we talk about astronomy in profession and research, we actually do something like this, right? We go to the observatories and we use a lot of computers in order to drive the instruments, control the telescope. And this is actually the acquisition time when we get the observations. Then we have a step where we need to do the data analysis, right? This means a lot of hours in front of a computer trying to dig into the data and understand what is going on. Okay? I tried a lot to break down this into a pie in order to showcase what are the duties of a professional astronomer. So take this with a grain of salt, because there can be differences. For example, what I show here is that a guy that doing a guy or girl, of course, that does observational astrophysics, right? So what would be the responsibility? First of all, it could be some administrative duties, peer review, teaching or mentoring, depending on the level, publishing. This is one of the mandatory things. Then you have to collaborate it locally with your group members or the institute members, and of course internationally. You have to keep updated with literature, writing, finding proposals, and trying to develop your own career path. And then you have a big part of the pie that has to do with observations and analysis. The actual observing part is kind of small. I mean, unless you are a support astronomer in a telescope, or your project is critically based on observation, so then you spend a lot of time at the observatories. These can be up to 10% of the time. So we do observe, but it's not the whole portion of what we do every day. The majority is actually around this. Actually, in this part, data reduction, cleaning scientific analysis, probably maintaining, developing simulation for people that are doing theory, they're doing a lot of simulations and they're using the appropriate software, and of course a lot of sitting back and trying to interpret what you see, right? Good. I also try to break down this process of data analysis into a flowchart in order to see how this is done, what are the components of this process. So we start first from data acquisition or collection. Data acquisition means that we go to a telescope, right, and we get the images of the data. Query means that we have a survey that provides images or data, and we query the database. Okay, the form of data can be anything from images, catalogs, ASCII tables, measurements, anything. So depending on the file types, we do different things. If we have images, we have a pre-processing. For example, this is, without being too technical, we need to correct for some errors in the images and to calibrate these images. Then we have data, we have to do perhaps some mining, we have to do some cleaning, we have to probably combine with other surveys. As I told you, we need to look into different parts of the spectrum, so we need to gather information from any possible source. And if you are working with synthetic data, this is a bit simpler at this step, because you're actually using a model, you're producing your data, and then you progress with the analysis. So it's you don't do something with the processing of the data because you are generating the data. So you have collected all of this, you have done some pre-processing, and then you actually enter the true analysis step. That is the place or the moment that you try to measure things, whatever it might be. Fit probably some of your data in order to understand what they are doing, and quantify uncertainties. This is a very basic step in science, especially in astronomy. Then after that, you need to interpret the results. What does it mean? Is that you need to compare either with theory, with a theoretical model, or with previous studies. How does my data, my results, compare with what X and Y person did in the past? Is it better? Do I see something different? Why? Actually, the answer is what's new in what I'm doing. Why am I doing that? And then we have the final step, which is to present this to some colleagues, to get some feedback, and of course, to publish or perish, as we say in this field, unfortunately, your results, right? Good. Within this scheme, do you see that Python fits some of these or any of these boxes? Obviously, I think you can see many parts. Data cleaning, filtering, pandas, right? NumPy, interpretation, analysis. You can use visualization tools. Anything, Matplotlib, Seaborn, right? Fitting processes, okay, scientific Python. For example, machine learning approaches in order to make predictions, classification. Query, you can use any query. Okay, you can use SQL indeed, right? But definitely you can use a lot of Python routines that are provided in order to do this. So as you see, there is a lot of room to exploit Python. And this is actually done. So below the main title, I have put this phrase, through a slight personal perspective. So I will just enter now my personal experience through this path. I started my PhD back in 2010. Back then, I didn't have any programming skills. Have you ever heard of Pascal? I didn't expect that. Okay. It was back in my university years that I learned programming in this language. I had some experience with C, but I wouldn't consider it really something like a tool. And at least what I was doing before astronomy, I was working with Origin, if you know, with something like Excel. So when I entered the astronomy field, the landscape was something like this. We would work with Unix systems, either MacOS or Linux distros. Fortunately, I was working already a few years with Linux only, so it was easy for me. And there was a lot of shell scripting. We would use a lot of bash scripts to do the analysis and, of course, to install everything, all the necessary tools, which was a pain, some of them. And you would do a lot of manual operations with awk, set, if that tells something to you. And there were people using IDL, which was a scientific programming language that had a lot of astronomical routines written on this. The problem with this language was that it was proprietary and had some cost. Okay, not significant, but you had to pay. Then there were some open source packages. One of them was Starling. Do you see the date? They started developing that in 1980s. And when I was looking about the story about this, I found this brochure. This brochure dates back to 1994, right? What you see here is an image, and in this image, I don't know if you cannot read that, but what it says that this software has managed to identify the sources automatically, right? And these are not cycles, and you can see that there are some ellipses, for example, that follow the shape of the object, and they made some flux measurements in this case. That was done in 1994, okay? Some of you were not born, and if you were born, probably you remember the floppy disk of 5 1/4, right? So, astronomy has pioneered some things, especially with respect to data reduction and software. Good. Now, another tool back in the time, which is still heavily used, is DS9, which was a visualization tool. This is an image of the tool. I will not go into the details. What you see is an image. This is a raw image of one observation. I don't remember exactly what it is. It says from Ogle in the Small Magellanic Cloud. Anyway, whatever, and you can see what you can do, like highlight some portions and measure the distance. This is just to show you the an image of DS9. Then we had many instrument and telescope pipelines, which were custom. And there was also what I would call the astronomical tool, what is famous as IRAF, the Image Reduction Analysis Facility, which was a general purpose software for the reduction and the analysis of astronomical data. That was also developed in 80s. And it has been, and actually it is in use up to now, right? I mean, the official support has decreased since 2013, but it is maintained by some community members. And this is an image of IRAF. This is a command language that tries to do all this processing, and this is it uses DS9 to visualize, for example, this image of the galaxy, and there you put a cursor and you try to measure, for example, what you call, probably this is the center of the galaxy, and you try to measure the, let's say, the flux density there. And this is a window that you can define some parameters. Okay, all of this was done manually back in the time. So I needed something else to work with. I needed some automation. I needed some flexibility. And also I would like to work with something which was open source, okay? Python 2, version 2, more or less, was there. And there were a lot of packages available, but they were kind of independent. It was a fragmented environment. Also, I actually lack any local support. I remember going around the institute back in 2010 and asking, do you know Python? Nobody was aware of Python, at least at the physics department, at least at astronomy group, in order to be fair. Perhaps in another division, they knew Python, and probably the computer science department knew about Python. But the problem was that I couldn't find somebody to depend or ask. My only help would be Internet and Stack Overflow, right? No AI, unfortunately, back then. So I took a leap of faith and I said, okay, I'm going to work with Python. I think this is the future, so I'm going to start working with Python with any hurdles I may face. And I started working with PyRAF, which is a Python wrapper for IRAF, and of course, standard libraries like NumPy, Matplotlib, and Scientific Python. This is one of the very early Python scripts, date May of 2010. Okay, Python 2, you see, print without any parentheses. It may sound weird, but that's the case. And then, very close, around 2013, we had the first release of AstroPy. AstroPy is a community effort to develop a common core package for astronomy, to include actually all astronomy-related packages. It was sparked by community need and collaboration in the field. The initial idea was back in 2011, and they managed to get to the first release within 18 months, mainly because they had a lot of pre-existing packages. It has been community-based in the sense that the community, a lot of students, postdocs, scientists, and professional software developers supported this effort. And actually, the support by the Space Telescope Science Institute was critical in order to make it a success. Of course, people try to include and foster the growth of broad community, and they were lucky because there was a rapid growth of GitHub and other open collaboration tools that help to put everything together. What AstroPy did, it managed to unify assess astronomy tools like Fitch handling, coordinates, etc., with the main Python ecosystem and include legacy packages. And this helping to create an interoperable library, allowing also affiliate packages, which means people independently developing packages that would follow the core idea of AstroPy. And there was also a series in Python, in Astronomy Conference series, that actually boost the use of Python. Now, where is Python used today? Before that, this is a list of of the native libraries. This is just a selection, right? It's not the whole ecosystem. And some names of Astro libraries which are very specific, like utilities for photometry or spectroscopy, specifically Astro machine learning, more based on astronomy-related things, PyHammer, which is a package to do spectral classification. So, where is Python used today? Almost everywhere. You can find it in the space telescopes, and not on the space telescopes, but as pipelines or calibration pipelines in the ground, like Hubble, James Webb, Gaia. You can find it in the largest ground-based facilities, Subaru Telescope, ESO in Chile, also Vera C. Rubin Observatory, the one that I showed from the images, and the Square Kilometer Array Observatory. These two will become more clear in a while. There's another field where Python played a critical role. It has to do with the era of big data and AI in astronomy. As surveys becoming larger and larger, the products are increasing in size. And that challenges a lot how we capture, clean, transfer, store, analyze, and visualize this data. And we'll show you some examples. Then it is velocity. How fast are these data generating? This is challenging how we do the processing of this data. And last, there is a huge variety. Various astronomical sky surveys include images, they include catalogs, they include measurements of any kind, flux, velocities. They may have also time in taking the same source observed in different epochs, and may have also simulation data. And some of them may have hundreds of features. And if you try to compare different surveys, you will see that they may have different formats. So this is kind of a challenging of how you do data integration and high-dimensional data visualization. So we'll show you now one example of Vera C. Rubin Observatory and why we're talking about big data. Do you see this? This is the largest CCD produced probably up to today. It is 64 centimeters in diameter, and it's about 3.2 gigapixels and produces 8 gigabytes per image. And this image is produced every 40 seconds. What does it mean? That within a night, you produce up to 20 terabytes. Okay, what is this is equivalent of 3 years watching Netflix in a night. Probably we cannot do that, of course. So this puts a lot of challenges. Every night, there are many of these exposures obtained. And not only that, within 60 seconds, we have to do all of this processing. I will not go through the list, doesn't really matter, but there is a lot of stuff like, for example, image characterization. You have to measure something for this. You have to do some image reduction. And this takes some time, but this needs to be compressed within 60 seconds, right? And not only that, this survey wants to produce some alerts. It looks at the sky, observes continuously, and there are many phenomena that we call transient phenomena. You see them once, or some of them can be repetitive, but the point is that you want to catch them at the right time. And in order to do that, you have some software systems called alert brokers. What they try to do is take let's say, the appearance of an object and transfer this information as fast as possible in order for other observatories to follow up with other observations. And in order to do that, you need to filter the alerts or cross-match with previous catalogs in order to identify if this is something new and important or not, and a number of other steps. And imagine that these alerts can be up to 10 million per night, and you have to do that for all of them. And this, of course, cannot be done else rather than use AI. Okay? Good. Now, let's go to another amazing example about big data, and probably it is the ultimate challenge of big data. So what do you think would be the data generation rate in this radio project? Any ideas, perhaps? Just any number, like, I don't know, 8 gigabytes per second. Okay, 1 to 2.5 terabytes per second. Okay, this is sorry, I don't know if that it is something like 45 years of non-stop 4K movie watching per second. This is huge. I mean, this is not feasible to do that. You cannot store this amount of data, right? The only thing you can do is try in real time and near live processing to do all the necessary steps and keep the final products. And in order to do that, they're going to use two science data processors, as they call, which is about 135 petaflops. And these are considered two of the, let's say, among the fastest computers existed back in 2020s. So you understand how important it is to use modern and actually develop new approaches in order to serve astronomy. Another example of big data is Gaia mission, which has resulted in 1.8 billion sources. Some of them has about more than 300 features, and you have also time series data, you have flux measurements in 3 different fields, you have spectra, and you can understand that there's a variety of features that you need to deal with. So I hope that I have actually convinced you that big data and AI is very important in astronomy. And of course, this is a challenge for modern astronomers. As astronomers or astrophysicists, we are actually trained a lot in the science of physics and the astrophysics needed. We do not get a lot of training with respect to computer skills that are needed, like coding. Python is a must. No. Data handling, storage solutions, AI tools, statistics, even statistics. The curriculum perhaps have one course, but this is not enough. Astronomy is data-driven and needs this training. To address that, me, along with some other colleagues, friends, actually, we initiated back in 2019 what we call Summer School for Astrostatistics in Crete. What we try to do is to train people that they know something and manage to convert them from basic practitioners up to professional practitioners on these topics. This is just a small presentation of the core of the program, what we try to do: classical, Bayesian statistics, Markov chain, Monte Carlo simulation, machine learning, deep learning, introduction, clustering, classification, and this is the core of our program. And at the same time, we try to spice it up every year with something new, like time series analysis, convolutional neural networks, diffusion models, GPU parallelization, Gaussian processes, even applications through citizen science. This in order to try to give an overview of the field and give them tools that they can use in their everyday research. So this is, let's say the core, the backbone of our approach. This is an intensive 1-week program, but it includes beach time, guaranteed. We have a small number of people because we are using a computer lab provided by the physics department of Crete, and we cannot fit more than 30 persons, unfortunately. But we do require in-person attendance in order to have the better facilitation of the school. Then it is totally hands-on. What it means, we have the minimal theory that is needed, but a lot of exercise in order to people get acquainted with the tools. And of course, we are using Python through Jupyter Notebooks because it is interactive and easy to share. We have the last years we have implemented Conda environments in order to avoid any unexpected troubleshooting. We just have the Conda environment installed. People they enter the Conda environment and they run exercise through this. We are using real data, of course, in order to make it more attractive for people. And we actually enforce pair coding. We saw that this works a lot because people get connected, they share in the network. And of course, it is an open science project, which means that all the repo is totally public and with an open license, which means that you can get it and use it, adjust it, and apply it to your own instance. So this is a bit of the statistics. What we have, the applications have received so far is more than 500. It's an oversubscription of 4. Unfortunately, we cannot accept all of them, but at the same time, it shows the need in the field. People, students especially, and early postdocs really need this training. We have managed to train a bit more than 150 students from 55 different institutes and 21 countries. And you can see the split around here. And also, it is very important that we get acknowledged for this work as people acknowledge us at the publications. And this is really cool. It shows that we actually have an impact in what they do. So, what's next? We saw that this, let's say, initiative worked. So we would like now to standardize. We have created this Astronaut Academy to work as a global open platform to teach statistics and AI tools with Python. Of course, the focus is in astronomy right now, but with help, we can easily expand this to other fields. For example, the code, let's say the basic core of what we do is the same, whether you do astronomy, whether you do biology, whether you do something else. An example of this is that we have the first international workshop outside Crete in this coming November, and we'll see. I mean, the future is in front of us. So these are the data, the information. If you want to come in to contact us, and then I would like to close my talk with some remarks. Right. So the first one, which is very important, very critical, is that tensors are functions. Right? This is what we need to get out of this conference. Then, Python does not bring code and nice tools only. It comes with an open, friendly, and inclusive community that allows everyone to join and contribute. This has allowed the development of so many tools and the impact in astronomy. We are very lucky in astronomy because we already have a very international and interconnection environment. Astronomy over the last few decades has become very dependent on the international collaboration. All these projects that I referred to previously, all the space missions, most of them are international. There are almost all countries involved. And it is also important because it also provides ideas of how you share data and knowledge. Okay, this is very, very important in the science community. And last but not least, I would like to think of Python as a way or as a tool that help us understand the universe, right? And this is the deepest image we have observed so far. This is a James Webb image back to about 4.6 billion years, almost around the time that the solar system was formed. That's all on my side.